So in the previous lecture we have seen how to find the electric flux, but the electric flux we define for only the suppose if this is the area vector and this is the electric field vector, right, or the S vector you can write. So what is the electric flux linked with this surface? You tell. E dot ds, and it is equal to Es cos theta, where theta is the angle between E and S vector. Are you getting or not?
Yes.
Right, but this is for, right, for open surface, for open surface. Are you getting or not? Listen, and here the electric field is what? Say constant. If electric field is variable, right, then what will you do? If suppose this is the surface and here the this is the ds vector and the electric field vector is E and this angle is theta. Are you getting or not?
Yes.
So if you consider this is the elemental portion, so the element for this elemental portion, everywhere the electric field is different. So if you are able to find the elemental electric flux is equal to E dot ds. Are you getting or not? You tell. This is the elemental electric flux linked with this elemental area, because everywhere if you consider here the electric field is different, here the electric field is different. So if you want to find the net flux linked with this surface, so what you have to do? Total flux will be found with the help of integration. That is integration of E dot ds. Is it clear or not?
Yes.
Tell me, is it clear or not?
Yes.
For example, I am giving you the example. Suppose this is the circle and this is the circle of radius r. Is it clear?
Yes.
And at distance x, the electric field is given as E naught x square. Fine. Where what is x? Where x is the distance, from center. Are you getting or not? Tell me. The electric field at the center is what? Say 0. As you are moving away from the center, the electric field is increasing. Are you getting or not?
Yes.
Then you have, and the electric field is in this direction, right? Electric field is perpendicular to the surface and which is varying as a function of x, right? Or instead of x you may write, it is better to write r square, where r is the radial distance from the center. You may write, right, is the radial distance from center, right? So then find flux link with this surface. Fine, link with this surface. Are you getting? For example, listen one thing. If it was the surface, listen one thing. If it was the surface, the radius is capital R. Fine, and the electric field is constant. If the electric field is constant, can you tell me? And the electric field is in this direction. What is the area direction? This is the area direction and this is the electric field direction. The angle between them is 0. So can you tell me what is the electric flux in this case? You will say Es cos theta. Why Es cos theta? Because electric field is constant everywhere, but in this case the electric field is not constant, rather it is variable. So if you want to find the electric flux here, so E into S is what? What is the surface area? Say pi r square. So it was the answer in the previous lecture we had discussed. But now this electric field is not constant. As we are moving away from the center, the electric field is changing. So now you have to find flux link with this surface. Do you understand the concept?
Yes.
So for the constant electric field, you will use direct this formula. But for variable electric field, you have to choose first elemental area, then elemental flux you have to write, and then integration you have to use, right?
Yes.
Copy this first. So how to solve this question, you tell? To find the total flux, you take R as a distance from the center, right? And you take an elemental ring of the width dr. Are you getting or not? Yes, tell me.
Yes.
So therefore, at this point, the electric field is E, which is equal to what? E naught R square. What is this area? You tell. The elemental area is equal to what? Say 2 pi r into width dr. Tell me, you are getting? So what is the elemental flux? Listen, this is the area ds vector, this is the electric field vector. The angle between them is 0. So elemental flux is equal to E dot ds cos 0. The electric field is E naught r square. The area vector is 2 pi r dr. So the elemental flux is E naught into 2 pi r cube into dr. Is it clear or not, you tell?
Yes.
So how to find? Listen one thing. I am making the cross. This is the side view. From the top view, at distance r, I had choose. This is the elemental ring, and because of this elemental ring, right, the elemental flux we know, right? Now there are so many elemental ring will be there. This is the elemental ring, this is the elemental ring, and this is the elemental ring. Are you getting or not, you tell? So this is the flux d phi linked with this. So if you want to add, if you want to find the net flux, what you have to do? You have to add all the flux linked with this elemental ring, which start from r is equal to 0 to r is equal to capital R. Are you getting or not?
Yes.
To find the total flux, you have, that is, you have to integrate this total flux E naught into 2 pi r cube dr from 0 to capital R. This is E naught into 2 pi r cube into dr from 0 to r, E naught into 2 pi r की power 4 divided by 4 from 0 to r. So the answer is E naught into, yes, this is the pi by 2 r की power 4 minus 0. 1 by 2 pi epsilon naught r की power 4 is the total flux linked with this surface. If it was constant, it was the flux. If it is variable, then it is the flux, right? Copy this. Now listen one thing. If surface is closed, right? Flux linked with surface which is closed. Suppose this is the closed surface, this is the spherical shell, right? If you consider some charge is placed inside this spherical shell, and the electric field is, this is the ds vector, and suppose the electric field vector is like this, right? This is the theta. So what is the elemental flux? So d is equal to E dot ds. Is it clear or not? How to find the total flux? Say integrating this E dot ds integration. Is it clear or not, you tell?
Yes.
Now listen, if this surface is closed surface, so everything is same, only the flux linked with this closed surface, this closed contour or the circle is placed in the integration. Is it clear or not?
Yes.
The difference, what is the difference between this? This is the integration of electric field with respect to surface. For open surface, not a big thing, but only the symbol, which is very important, right? Sometime it may be asked in the examination. It represent for closed surface. Are you getting or not? So this is the total flux. This is total flux linked with closed surface. Is it clear or not, you tell?
Yes.
So this is only the symbol difference. For open surface this, for closed surface this. Copy this. So now I will write the Gauss's law. What is the Gauss's law? You tell. Gauss's law. According to Gauss's law, I am not writing the definition. According to Gauss's law, if these are the some charges like this is Q1, Q2, Q3, Q4, Q5. This is the one closed surface, right? And this is the another closed surface. This is surface S1, this is surface S2. So according to Gauss's law, the net outward flux is equal to, right, charge enclosed divided by epsilon naught. What is the net outward flux? Net outward flux is equal to charge enclosed divided by epsilon naught. This is called the Gauss's law. Is it clear or not? Right? If you consider this the surface S1, right? Surface S1. So what is the net outward flux? This is the net flux linked with the, because net outward flux linked with closed surface. It is very necessary. Linked with closed surface is equal to charge enclosed divided by epsilon naught. So what is the net outward flux linked with closed surface? E dot ds is equal to Q enclosed divided by epsilon naught. Whenever you are writing the Gauss's law, it is always for closed surface, not open surface. That is why this circulation comes over here. Is it clear or not, you tell?
Yes.
For surface S1, question is for surface S1, flux. How to find the flux? E dot ds for surface S1 is equal to charge enclosed divided by epsilon naught. So suppose this is the 1 microcoulomb, suppose this is the 1 coulomb, this is 2 coulomb, this is 1.5 coulomb. Is it clear or not, you tell?
Yes.
This is minus 1.5 coulomb, and this is minus 2.5 coulomb, and this is 6 coulomb. So can you tell me for this surface what is the charge enclosed? Please tell.
The 1 plus 2 plus
1.5. 1 plus 2 plus 1.5 divided by epsilon naught. So this is equal to 4.5 divided by epsilon naught. This is the flux link with surface S1. For surface S2, what is the flux link with that? S2, this is the representation, is equal to charge enclosed divided by epsilon naught. Yes, this is the surface S2. Fine. What is the charge enclosed, you tell? 1.5 plus 6 minus 2.5 upon epsilon, right? So this is 4, this is how much? 5 upon epsilon. Is it clear or not, you tell?
Yes.
Right? This is the 5 upon epsilon naught. So this is the Gauss's law. So Gauss's law is always defined for, first of all,
Closed surface.
and this is the representation of flux linked with this closed surface. This is for open surface, right? Copy this. So the application of Gauss's law we can see, right? The application first. Although the Gauss's law is valid for everywhere, but still we will use for symmetric charge distribution, right? We will use this for symmetric charge distribution. Still it is valid for all types of charges, but we can find electric field, right? We can find electric field for symmetric charge only, symmetric charge distribution. Fine.
Yes.
So for example, first this is electric field due to point charge. right? Electric field due to point charge. For example, listen one thing. This is the plus Q, and due to this point, we have to find the electric field at distance r. Are you getting? So this is the electric field, right? So we will choose a Gaussian surface. All right. This is the Gaussian surface. So this is the electric field. Are you getting or not? So to find the electric field at this point, what will you do? You will choose an elemental area. This is the ds area. Because of this, the electric field is, if you choose this is the ds vector, so the electric field vector in this direction. Is it clear or not, you tell? Right? So the theta is what? Always 0. Because of this plus q charge, the electric field always symmetric, like this. If you draw the circle, the electric field at this point will be 0 always. Are you getting or not? Right. So now apply the Gauss's law. Apply Gauss's law. What is that? The net outward flux is equal to charge enclosed divided by epsilon naught. So what is the charge enclosed? This surface Q. And what is the net outward flux? Say E dot ds. Is it clear or not? E dot ds, what is the angle between the electric field and ds vector? Cos 0. Cos 0 is 1. So it may be written as E ds q upon epsilon naught. Is it clear or not, you tell? The electric field everywhere is what? Say constant. It is constant. So it comes out from the integration. Right. And this is the surface S. Right. This is the surface S. Q upon epsilon naught. Yes. Can you tell me what is this integration? What is this integration? Tell. Listen. It is R. This is the elemental ds. The integration mean all the ds you have to add, all the ds. So if you add all the ds, it means the surface area of the spherical shell you have to get. So this integration is nothing but area, total surface area. Not getting. Ds is equal to s is equal to 4 pi r square, total surface area, right? Q upon epsilon naught. Electric field is Q upon 4 pi epsilon naught r square. Is it clear or not, you tell?
Yes.
Copy this. So listen one thing. For example, the electric field due to non-conducting uniformly charged sheet having linear charge density lambda coulomb per meter, right? What does it mean? Suppose this is the sheet, right? This is the sheet, non-conducting sheet it is. If you have given the charge, right, infinite long mean like this. This is the sheet, right?
Yes.
Up to infinite, right? And the sigma, having sheet having surface charge density sigma coulomb per meter square. Its density is sigma coulomb per meter square. Are you getting or not? So at this point, you have to find the electric field. You will choose a Gaussian surface, right? This is the horizontal cylinder. You are choosing the Gaussian surface. Are you getting or not? Due to this symmetric charge distribution, the electric field will be E over there. The electric field will be E over there at the same separation it is, right? So if you consider this is the area S1, this is the area S2, right?
Yes.
And this is the lateral surface. Suppose this is the cylinder, right? This is the one surface, this is the another surface, this is the lateral surface. So for this lateral surface, the ds vector is in this direction, right?
Yes.
And the electric field is this way. So this is S1, S2, and you assume this is the lateral surface S3. So for this case, for S3, what is the angle between the electric field vector and the ds vector?
Yes.
90 degree,
Yes.
right? And what about this? This is the surface area, this is the electric field. So what is the angle over here? 0. If you consider this the electric field, this is the S vector, the angle is 0. Are you getting or not?
Yes, sir.
And you consider this is the cylinder. Here, this is the charge, right? This is the charge enclosed by this cylinder. Are you getting or not?
Yes.
If you consider the area is S, this is also S, this is also S. So what is the charge enclosed here, you tell? What is the charge enclosed? Sigma coulomb per meter square mean in 1 meter square the charge is
Sigma.
sigma coulomb. So therefore in S the surface charge is S into sigma. So this is the charge enclosed, right? So here what is the charge enclosed is equal to sigma into S. You understand this or not?
Yes.
Now apply Gauss's law. What is the Gauss's law? Outward flux is equal to charge enclosed divided by epsilon naught. Here, what is the Gaussian surface? This is the horizontal cylinder. So in this horizontal cylinder, what is the charge enclosed? This is sigma into S. Is it clear or not, you tell?
Yes.
Copy this first. Now what is the flux? Outward flux. The flux link with this surface. Flux link with this surface. What is the flux link with this surface, you tell? The phi 1, phi 2 plus phi 3 is equal to sigma into S upon epsilon naught. What is the phi 1? Say ES. This is the open surface now. It is open. Although this is the closed surface, this all closed surfaces converted into 3 open surfaces. E dot ds, S1 E dot ds, S2 E dot ds, S3 is equal to sigma S upon epsilon naught. For this, what is the electric field, electric flux? Say E into S. For this surface, E dot S. For this surface, 0. Sigma S upon epsilon naught. 2Es, sigma S upon epsilon naught. SS will cancel out. Electric field is sigma upon 2 epsilon naught. Right? Copy this fast. So this is the electric flux, electric field due to conducting sheet. Right? Now we will discuss the electric field due to electric field you have to find due to conducting sheet. Conducting sheet. Right? What is the difference between conducting and non-conducting sheet? Having surface charge density sigma coulomb per meter square. The property of the conductor is that the surface, the charge resides on the both surfaces. If it is the conductor, right? Suppose this is the iron sheet. The properties of this sheet is that the charge will be on this side also in this side, right? It is never possible that the charge on the sheet is always on the one side. Charge is always on both sides. Suppose this is the sheet, right? This is the infinite sheet, like this. This is the sheet. Are you getting or not? So if this is the sheet, the charge on this side is sigma coulomb per meter square. This is also sigma coulomb per meter square. Fine. Are you getting or not, you tell?
Yes.
Now you will consider, you have to find the electric field at this point, distance r. Consider a cylinder now. in the same way, previous problem. So in this case, by the Gaussian surface, this is the charge. If this is the surface S, this is the S, this is the charge enclosed, this is the charge enclosed. Here the electric field is in this direction, here the electric field is in this direction. If the electric field is same at distance r, so what is the flux phi1 linked with this? Say E into S, because theta is 0. Also if it is S vector, the electric field is in this direction. What is the flux linked with this? Say E into S. Are you getting or not?
Yes.
If you consider the lateral surface again, this surface vector and the electric field vector at 90 degree. So what is the flux linked with this lateral surface? 0. Are you getting or not? Now you will consider the E dot ds is equal to charge enclosed divided by epsilon. This is what? Gauss law. So what is the charge enclosed? You tell. This charge and this charge. If the sigma coulomb per meter square the surface charge density, so sigma into S plus sigma into S. Please tell, you are getting this thing or not?
Yes.
So this is 2 sigma S upon epsilon. The electric flux phi1 plus phi2 plus phi3. This phi3 is 0 ES plus ES is equal to 2 sigma ES, 2 sigma S upon epsilon. So 2 ES is equal to 2 sigma S upon epsilon. Not SS will cancel out, 2 will cancel out. The electric field is sigma upon epsilon. Alright, copy this. So the next application of Gauss's law, the electric field due to uniformly charged shell, right? Suppose this is the shell and the charge is q over the surface. Are you getting or not? You tell. The radius is capital R. So you have to find the electric field from R is equal to 0 to capital R, right, as a function of R. So there will be the two cases, right? Case 1, inside mean the point is inside, the radius you may assume capital R. If you want to find the electric field at the point P at distance R, is it clear or not? You tell.
Yes.
Then you will choose a Gaussian surface and apply the Gauss's law. The outward flux linked with this closed surface is equal to charge enclosed divided by epsilon. Okay, if this is the total charge on the surface of the spherical shell, what is the charge inside this Gaussian surface? You tell.
It is
0. No. All the charge, suppose football. On the surface, the charge is on football. But if you consider the spherical shell inside the football, so what is the charge enclosed by this small spherical shell? 0. So charge enclosed is 0. So if electric field, if you take outside, so although the integration, suppose this is the point P, this is R, this is the ds vector. So what is the integration of this ds vector? The surface of this small spherical shell, this is 4 pi r square is equal to 0. The electric field is 0. What does it mean? It means from r is equal to 0 to capital R, 0 to capital R, inside the electric field is 0. Now we consider the case 2, outside. What does it mean outside? The value of R is greater than capital R and less than infinite. For example, we have to find the electric field at point P at separation R from its center. Are you getting or not? You tell.
Yes.
To find the electric field, and this charge is symmetric. So we will choose a Gaussian surface like this, right? And the electric field is E. So if we apply, the net outward flux is equal to charge enclosed divided by epsilon naught. So this is the spherical shell, Gaussian, this is the Gaussian surface. What is the electric field? What is the net charge enclosed by this Gaussian surface is equal to Q. Are you getting or not?
Yes.
And the electric field everywhere is 0 if you choose this is the ds vector. The E vector and ds vector are in same direction. So the theta is 0. So if you write this in this way, are you getting or not? So
Yes.
if this is the elemental area of this Gaussian surface, so what is the integration of ds? That is the integration total area of this is equal to 4 pi small r square upon epsilon naught. So electric field is 4 pi epsilon naught r square, right? Copy this. So this is the electric field as a function of r, q upon 4 pi epsilon naught, and this electric field is inversely proportional to r. What is the value of r outside? Capital R to infinity, right? So here I am writing after this, r varies from capital R. At r is equal to capital R, the electric field is q upon 4 pi epsilon naught r square, right? That is on the surface, the electric field is what? Kq upon r square. This is k, kq upon r square. Is it clear or not, you tell?
Yes.
And outside, if you consider r is equal to infinity, r is increasing up to infinity. So here r is equal to infinity. If you put infinity, what is the electric field at infinity? Is it understood or not, you tell?
Yes.
This is the electric field at distance r. At infinity it is 0. So how it is varying? It is varying like this. Electric field inversely proportional to r square. So in the shell, uniformly charged, the inside electric field is 0, then it decreases in this way. Is it clear or not? Copy this. So now with the help, this is the another application of the Gauss's law. The sixth application it is, it may be sixth or fifth. The electric field you have to find due to solid non-conducting uniformly charged sphere, right? Uniformly charged sphere. Non-conducting mean if you consider the sphere and the charge is distributed over the volume, this is the total charge, right? The charge is distributed over the volume, right? Where you give, if you give the charge to this volume, the charge will remain intact, right? Instead, if you consider this the conducting, right? Suppose this is the copper sphere, and if you give the charge to this, so the property of the conductor is that the charge will come on its surface. Is you understand or not? Right? So this is the non-conducting spherical sphere, and the charge is distributed over its volume. So you have to find the electric field. Also you have to draw the graph of the electric field inside the sphere, right, and outside the sphere, right? So we will have again the two cases. First, case 1, inside, right? Inside mean the point I will choose from 0 to r at this point. This is the distance r, the total radius is capital R, right? At this point, if we want to find the electric field, I will choose, this is a Gaussian surface, all right, and suppose the electric field at this point is E. Every point at this point the electric field be E, and this is the inside volume, right? So this is the Gaussian surface. So now you can apply the Gauss's law. What is the Gauss's law? The net outward flux is equal to charge enclosed divided by epsilon naught. So first, what is the outward electric flux? Say E dot ds is equal to charge enclosed divided by epsilon naught. So can you find the charge enclosed in this volume? Yes. How this charge is distributed? The charge is distributed over the volume. So to find the charge on this volume, that charge will be less than capital Q, that is distributed over the 4 pi, right? In 4 pi r cube, the charge is distributed Q. So 1 meter cube, the charge is divided by 4 pi r cube. This is the unitary method I am using. So in this volume, how much it is? 4 by 3 pi r cube volume. The charge is 4 pi by 3 r cube into 4 by 3 r cube, right? So this is the charge enclosed, Q upon r cube into small r cube. Is it correct or not? Right. So now I can put the value of charge enclosed, Q upon capital R cube small r cube, right? It is equal to Q upon r cube upon epsilon naught. Now E dot ds, if you consider this the electric field, the ds vector in the same direction, theta is 0, right? Theta is 0 degree, so E will come outside the integration ds, Q upon r cube epsilon naught, right? What is the integration of ds? This is our Gaussian surface. This Gaussian surface is a shell, right, or a sphere of radius r. So if you consider the elemental ds vector, small elemental area over the surface, so if you integrate this, the total surface area, the integration of ds is total surface area, which is equal to 4 pi r square, Q upon r cube upon epsilon naught. So r square will cancel out, 4 pi Q upon r cube into r upon epsilon naught. If you simplify this, qr upon 4 pi epsilon naught capital R cube, right? So this is the electric field inside the right sphere. Copy this. So now you can make the graph. The electric field here is variation directly proportional to r. At r is equal to 0, mean at its center. If you put r is equal to 0, what is the electric field? 0. The value of r is varies from 0 to capital R, mean inside we are talking about. So on the surface at r is equal to capital R, right, at this point, the electric field is kqr upon 4 pi epsilon naught r cube is equal to q upon 4 pi epsilon naught r square, and this is equal to kq upon r square. So on the surface, listen one thing, an electric field is directly proportional to r. So inside, the electric field varies proportional to r. At r is equal to 0, the electric field is 0. At r is equal to capital R, the electric field is kq upon r square, right? So this is the variation of electric field inside the non-conducting uniformly charged solid sphere. Copy this first. So this is the inside, and now I will find the outside. For the outside, case 2, outside. Outside mean the value of r is greater than r and less than infinity. It means if this is the sphere and this is uniformly charged sphere, right? The outside mean at this point you have to find the electric field n. This is the distance from center to this point, P is r. So to find the electric field, you will choose a Gaussian surface, and the electric field at this every point will be what? Same. And this is proposed in this direction, right? If you choose, this is the direction, right? So apply the Gauss's law. What is the Gauss's law? The net outward flux is equal to charge enclosed divided by epsilon naught. Q outward flux is equal to charge enclosed divided by epsilon naught, right? This is the Gauss's law. What is the enclosed charge by this Gaussian surface? Tell me. Total charge. This is the total charge. Complete charge is enclosed. So enclosed charge is Q upon epsilon naught. The electric field will be constant everywhere and integration of ds. Now this is the small ds element and this is the sphere, right, of the radius small r. So what is the value of integration of ds? Say it is 4 pi small r square or capital R square?
Sir, capital R square.
No. This is the Gaussian surface. This is the Gaussian surface. And we have chosen the ds area. So if you integrate this, which surface area you are getting? 4 pi smaller square. When you choose the Gaussian surface over here, when you integrate this ds, which surface area you are getting? The surface area of Gaussian surface. Again here is 4 pi r square. But r is outside, so here it is 4 pi small r square. Q upon epsilon naught. Electric field is 1 upon 4 pi epsilon naught. Q upon r square is equal to kq upon r square. So electric field as a function of r is proportional to 1 upon r square. R value varies from capital R. On the surface, the electric field is kq upon r square and values up to infinity. That is, at r is equal to, on the surface, on this surface, this is the electric field, and at infinity, the electric field is what? Say 0. Right? So if you draw this graph, the graph is like this. Electric field is proportional to 1 upon r square. This is outside. Fine. Copy this. So now we discuss some cube problems in Gauss's law, using the Gauss's law. First example, suppose this is the charge, right? If this charge is placed, this is the cube, right? And the side of the cube is suppose the A, and if the charge is placed at its center, getting or not? Charge is placed at the center, you have to find the flux linked with cube and one phase, right? So this is the question. So how to solve this question? Listen one thing. Yes, tell me, if you apply the Gauss's law, what is the Gauss's law? The net outward flux is equal to charge enclosed divided by epsilon naught. If you assume this is the cube, assume to be the this is the Gaussian surface, right? If you assume this is the Gaussian surface, are you getting or not?
Yes.
So what is the charge enclosed in this cube? Say capital Q. So this is the net outward flux. So the total flux linked with cube, total flux linked with cube, what is that? Say Q upon epsilon naught. Are you getting or not?
Yes.
Now if you want to find the flux linked with one phase, can you tell me what is the flux linked with one phase?
So with one phase, so it will be Q by 6.
Epsilon naught. Yes. How to do this? Listen one thing. If you consider this is the flux linked with one phase like this. Suppose this is the phi dash. Since this charge is Q is placed symmetric, so what is the flux coming out from this phase? The same flux will come out from this phase, right? Like this. And therefore the same flux will come out from this phase. Is it clear or not? Phi dash. So how many phases are there? 6. So 6 phi dash is nothing but the total flux coming out from the cube, which is equal to this. So what is the phi dash? Q upon 6 epsilon, right? Copy this. Now in the second case, if you consider the charge is placed on the one phase, in the mid of the one phase, then what is the flux linked with this cube? You tell. Yes. How it is? Listen. To find the net flux, you have to draw an imaginary cube towards its right side, right? Like this. Are you getting or not? So if you consider what is the total flux linked with this cube, suppose this is the phi dash, this is the phi dash, right? And the same flux will coming out from this, right? Like this. It is phi dash. So phi dash plus phi dash, total flux linked with this charge enclosed divided by epsilon naught. What is the total charge Q? upon epsilon naught 2 phi dash. So phi dash is what? Q upon 2 epsilon naught. So this is the total flux link with this 1 cube only, right? Copy this. So what is the third case? If you consider the cube, this is the cube and the charge is placed at this one corner, then what will you do? Instead of one corner, what you have to do, put the charge on the one edge, right, like this, the mid of the one edge. Are you getting or not? You can put over here. If this is the charge placed, suppose at the one edge, what is the flux link with this cube? You tell. How to solve? Listen one thing. If this is the cube, a small cube, you can make this the charge, right? So if the flux link with this cube, we have to find, assume this the phi dash. So if the another cube just below it, you can assume. Are you getting or not, like this? So if this is the capital Q, what is the flux link with this cube also? Tell me. It is also phi dash, right? And these are the two cubes, and two cubes you can assume to be in front of this. So phi dash, and phi dash plus phi dash, right? So and it will be enclosed by this Gaussian surface. So net outward flux is equal to charge enclosed divided by epsilon naught, and the charge enclosed is by, say, Q upon epsilon naught. What is the total flux? Say 4 phi dash is equal to Q upon 4 epsilon naught. So the flux link with this one cube is what? Phi dash is equal to Q upon 4 pi epsilon, right? You can make. Okay, so in the next example, where we will put the charge on the one corner at this side, then what is the electric flux link with this cube? How to find? Suppose this is the one cube, charge is placed over here. The flux link with this cube is supposed to be, yes, this is phi dash or not, you tell. You can assume the one cube in like this in its right neighbor, and this is the one cube just below this, one cube just below this. So if the flux phi dash is going here, the phi dash is linked with this face, phi dash is linked with this cube, phi dash is linked with this cube. So these are the four cube, but this charge Q is placed in midwin. So the 4 cube we can assume in front of this. So total flux will be equal to what? So 8 phi dash is equal to charge enclosed divided by epsilon naught. So Q upon epsilon naught, 8 phi dash. So the phi dash is Q upon 8 epsilon naught, right? Copy this. Now the very important case, if consider if this is the cube, right, and this is the cube and the charge is placed over here, right? So listen one thing, if you consider the base face, right, suppose this is the face, it is in a plane like this and the charge Q is placed over here. Can you tell me what is the flux link with this face? Flux link with this face. Listen. No, listen. This is the face and the electric field is going in this way. The electric field line passing through this face in the plane of the square face. And what is the area? You can consider this the area vector or S vector, whatever you write, and the electric field is always perpendicular. So if this is the face and the electric field is in the plane of this face, the area vector is this and this is the electric field vector. So what is the flux link with this face? You tell. Say 0, right? So if this is the charge q and if you consider this is the face also, so there are three phases. This is the one phase. If you consider this is the charge q, right? So in this charge the electric field is again, for this phase the electric field is again passing through in the plane of the face. Are you getting?
Yes.
And also if you consider the front phase, this is the front phase and this is the charge q and the electric field is passing in this way and this is the vector, right? So this is the charge q and there are how many phases? 6 phases are there, all right, out of which 3 are touching phase. This is the touching phase, the side phase is touching and the front phase is touching. So out of the 6 phase, 3 are touching phase. 3 touching phase. And what is the electric flux? Flux linked. What will you say? 0. So the flux linked with 3 touching phase is 0. Are you getting or not?
Yes.
Now if you consider the remaining phase, so for this remaining phase like this, how many phases are remaining? 3. 1, 2 and the behind one. And these 3 phases are non-touching phases. Non-touching phases. Is it clear or not?
Yes.
So the question is find flux linked with touching and non-touching phases. Touching and non-touching phases, right? As shown in figure. As shown in figure. What is the figure? The figure is this. This is the charge q. The charge q is placed at the one corner, right? Copy this. So let me explain.
2 by 3.
No. Let me check. You tell me. What is the flux linked with this cube? You tell. The previous question we have done. What is the flux linked with this cube? Tell me.
It will be 2 by 8.
8 epsilon naught. Are you getting or not? So if you consider this is the one flux, this is the one phase, right? So if you consider this is the phase, right? Suppose this is the phi double dash. So as this is the phase, similarly this phase is symmetric with respect to this charge. All these non-touching phases, this is the 1, this is the 2 and the third is the behind one. So in the same way the flux will be passing through F double dash and flux the third one passing through the third one also passing through the phi double dash. So what is the total flux? Phi double dash plus phi double dash plus phi double dash is equal to total flux is equal to what is the total flux linked with this cube? Say 8 epsilon. So what is the phi dash? Phi double dash is the flux linked with one phase, one non-touching phase, non-touching phase, because flux linked with touching phase, flux is equal to 0 with touching phase. Is it clear or not? You tell.
Yes.
This is the thing. Copy this. So one more question related to the Gauss's law, similar type. Suppose this is the right square phase, right? This is the square phase and the side of the square is A, right? From its mid there is a charge capital Q. Are you getting or not? And this distance is at A by 2. You understand or not? You tell, right? So therefore if this distance is or you can put this charge, right, above this. Suppose this is the face of the side and the charge q is placed at distance a by 2. This is the charge. So look at the figure. The electric field will be passing through this face. So can you find the flux linked with face, square face? Tell me, what is the answer you will say? Listen one thing. How to solve this question? If this is the charge q over here at distance a by 2, right? So you can assume that there is another face like this, right? Like this. There is another face like this. Assume this is the one face, we have to find the flux. You can, sorry, what is this? Sorry, this is the one face, right? Now you can think this is the charge q, right? It is at distance a by 2. So you can assume this is also distance a by 2, a by 2, a by 2. So now this charge is in the middle of the center of the cube.
Yes, sir.
So what is the total flux linked with this cube? Total flux is q upon epsilon naught, or you tell.
Yes, sir.
Now, yes, now only we have to find what? We have to find the flux linked with one face. So suppose this is the phi dash, this is also phi dash, this is also phi dash, phi dash. So 6 phi dash is equal to q upon epsilon naught. So what is the flux linked with one face? 6 epsilon naught. So although they will not give the cube, they will give a face, and at distance a by 2, the side of the square is what? Say it is a, and they are asking the flux linked with this face, only one face. So you have to assume all the things by yourself, right? And then the flux linked with this, right, surface is phi dash is equal to q upon 6 epsilon,
Yes.
right? Copy this. So listen one thing. The another application which is very important. Suppose this is the line charge, right? Line charge. This is line charge having linear charge density. It is lambda coulomb per meter. All right. So because of this linear charge density, the electric field will be away from this charge, right? Suppose this is the distance r and you have to find the electric field at this point P. So to find the electric field due to this infinite line charge, we will use the Gauss's law. To find the electric field, we will assume a Gaussian surface which is the symmetric vertical cylinder. You can assume the length of this vertical cylinder is L. So if this is the closed surface, you can assume. So how many surfaces are there? This is the S1, this is the S2, and this is the lateral surface S3. This is the S1, S2 and S3. Are you getting or not?
Yes, sir.
At the lateral surface, the electric field will be same and away from the, right, away from the surface. Is it clear or not, you tell?
Yes, sir.
This is the side view. If you see from the top view, if you are seeing from here, right, this is the cross section, this is the line charge, and the electric field is away from this line charge. Are you getting or not?
Yes.
Like this. Look at the figure. The electric field at this point is E over here, at this point is E over here, at this point is E over here, like this. This is the electric field, this is the electric field vector. Are you getting or not?
Yes.
So now to find the electric field at distance r from the infinite line charge, we will apply the Gauss's law. You tell me, what is the Gauss's law? the net outward flux is equal to what? Charge enclosed divided by epsilon naught, right? So if this is the vertical cylinder is the Gaussian surface, what is the charge enclosed? This is the charge enclosed or not, you tell?
Yes, ma'am.
This charge is outside, this charge is outside. So if the length of the cylinder is L, this lambda coulomb per meter, what does it mean? It means in 1 meter, yes, in 1 meter lambda coulomb charge is present. So in L meter, what is the charge? Say lambda into L. So the charge enclosed will be equal to lambda into L. Is it clear or not?
Yes.
So this is lambda L upon epsilon naught. Now what is the outward flux? Say E dot ds is equal to lambda L upon epsilon naught. This is the flux linked with this closed Gaussian surface. All right.
Yes.
But if you consider this the surface S1, the area vector is in this direction, electric field is like this. So what is the flux linked with this surface? Say 0,
Yes.
because electric field is in the plane of this, electric field is plane in electric field is in the plane of the circular surface, that is the area vector is perpendicular to electric field, right? In the same way, this is the S2 vector and the electric field vector is in this direction. So here theta is again 90 degree and the flux linked with this surface is 0. Are you getting or not? So the total flux linked with this cylinder, right, surface as is equal to phi 1 plus phi 2 plus phi 3 is equal to lambda L upon epsilon naught. So phi 1 and phi 2 are 0. So this is, suppose this is the cylinder, this is the lateral surface, this is the cross section. So through this cross section, the electric field is parallel to the circle, so the electric field is 0. But for this surface, the electric field is coming out from the cylinder, curved surface. The electric field is perpendicular to the curved surface. That is, if you assume this is the ds vector, the electric field vector and ds vector are in same direction. So what is the flux phi 3? Is nothing but electric field into area. E, what is the area of this lateral surface, you tell? Area of this lateral surface is 2 pi r into L. 2 pi r into L. Please tell, is it clear or not, you tell? This is the cylinder, lateral surface.
Yes.
So to find this area, length is 2 pi r. Sorry, this circumference is 2 pi r. Length is L.
Into it. Yes.
So phi 3 is E into 2. So phi 3 is equal to lambda L upon epsilon naught. This is E into 2 pi r. L is equal to lambda L upon epsilon naught. L will cancel out. 1 upon 2 pi epsilon naught lambda upon r, right? The k value is 1 upon 4 pi epsilon naught, right? That is 2k is equal to 1 upon 2 pi epsilon naught. So the electric field, I will write 2k lambda upon r, and this electric field you have to remember, right? Electric field is inversely proportional to distance due to this infinite line charge, right? Copy this. So listen, one more thing. Due to the infinite line charge, we have seen the electric field is 2k lambda upon r. You have to remember. Now the electric field due to finite length, finite linear charge, finite line charge, right? Finite line charge mean it is not infinite, rather the linear charge density is lambda coulomb per meter, and this is of finite length from A to B, right? If you consider this the point P, a distance r, right, and this angle is making angle theta 2 and this angle is making angle theta 1. So the electric field you have to find at this point. So at this point the electric field will be in this direction and also in this direction, right? If you assume this is to be x, this is to be y, so here the electric field will be in the x direction, in the y direction. There will be the two component of the electric field. Is it clear or not, you tell? So the x component electric field is what? K lambda upon r, k lambda upon r sine theta 1 plus sine theta 2. Fine. Ey is equal to k lambda upon r cos, right, cos theta 2, theta 1 minus cos theta 2. Is it clear or not, you tell? Copy this first, then I will give some example. If wire is infinite, wire is infinite mean this end is going towards the plus infinity, this end is going to the minus infinity. So if this angle is what? Increasing, so it become 90. If this line charge is increasing, so this angle is what? Say increasing, so it is slowly increasing. In the same way, it is what? It is increasing, right? For if the wire is infinite, so theta 1 and theta 2 tending to 90 degree, right? It means it is tending to 90 degree like this. If this is the wire, so this is the 90 degree. What is the electric field in x direction? Sin 90 plus sin 90 become 1, 1 plus 1, 2 k lambda upon r. Are you getting or not? While the y component cos 90, it become what? 0. So no y component, only the x component is there due to this infinite wire. And due to this infinite wire, we have found the electric field with the help of Gaussian surface, Gauss's law also. The electric field comes to be 2 k lambda upon r in this direction, right? And here the y component is 0. Is it clear or not, you tell?
Yes.
Copy this. For semi-finite, yes, for semi-infinite wire, right? Semi-infinite line charge. What does it mean? The line charge starts from here and goes to the infinity. Is it clear or not? You tell. So it means this is the point at perpendicular distance r, you have to find the electric field. In this case, listen, this is the theta 2 and the theta 2 become, if it is infinity, so theta 2 become 90 degree. Is it clear or not, you tell?
Yes.
And what about the theta 1? It reduces to, if it was the point A over here, angle is reducing, and at this point, if this point A shift to this point, what is the value of theta 1? 0. And the theta 1 is 0. Is it clear or not, you tell first?
Yes.
So therefore, the electric field in x direction, what will you write? Sine 0 plus sine 90. K lambda by r 0 plus sine 90. Sine 90 is what? 1. So what is the value of Ex? It is k lambda upon r. Fine. And because of this charge, the y component will also be there. K lambda upon r, yes, tell me, cos 0 minus cos 90. Cos 90 is 0 and cos 1 is 1. So this is also equal to k lambda. You understand this thing or not, you tell? Now see, you have to remember also the result. If this is the infinite line charge, semi-infinite line charge at this point at distance r, this is the component of the electric field, say K lambda upon R, and this is also the electric field K lambda upon R. So what is the net electric field at this point? Say K lambda upon R root 2. And at what angle it is? Say 45 degree. This is 45 degree. You have to understand and remember this, right? Copy this. So read this question. In this question, there is a conductor. The properties of conductor you should know. If this is the minus q charge, the free electrons are available, right? So because of this repulsion, the free electrons go this side and it will attract equivalent positive charge. Is it clear or not? It was neutral. The electrons are drifted to this side, so equivalent positive charge appear, and this is the conducting sphere. You tell. You understand this or not?
Yes.
Now if you assume an imaginary Gaussian surface is this, right? This is what? Closed Gaussian surface. Closed Gaussian surface. Is it clear or not? You tell.
Yes, sir.
So in this closed Gaussian surface, what is the outward flux? Is equal to charge enclosed divided by epsilon naught. So the charge enclosed is what? Say minus q, suppose. So the outward flux is negative. What does it mean? The flux is not outward linked with this surface, rather flux is inward. Flux is inward or coming to the closed surface. Is it clear or not? So they are asking what is the nature of electric flux. The electric flux is negative and therefore it is coming towards the Gaussian surface, right? Copy this. So read this question. In this question, there are two concentric spheres S1 and S2, right? And the charge is enclosed. Suppose the charge is enclosed is Q and this is 2Q. It means it is the charge enclosed, right? So what is the ratio of electric flux passing through S1? Tell me. The flux phi1 linked with S1, right? Flux linked with S1 is equal to what? Charge enclosed divided by epsilon naught. So Q upon epsilon naught. Is it fine or not? You tell.
Yes.
While the flux linked with S2, phi 2 is equal to charge enclosed divided by epsilon naught. If this is the S2, what is the charge enclosed? Say Q and 2Q. So total charge is what? So this is the flux linked with. So what is the ratio phi 1 and phi 2? You tell. Q by epsilon naught, 3Q by epsilon naught. The answer is 1 by 3. Is it clear or not? You tell. Right. Now in the B part, what they are saying? What will be the, how will the flux S1 if the medium of dielectric air is introduced in the space within S1 in place of air? So listen, the electric field is 1 upon 4 pi epsilon naught Q upon R, if you remember, in the air or in the vacuum. But if some dielectric medium is placed, so it become, right, it become ER times. So the electric field, if you assume to E naught, so E dash become E naught by ER. So electric field is reduced by ER times. Is it clear or not? So therefore the electric field is reduced by ER times. Therefore flux is also reduced by ER times, right? 1 upon ER times. Is it clear or not? Copy this. So read this question. In this question, suppose the electric field as a function of x is given as alpha root x, while y and z direction electric field is not present. Alpha value is given as 5. So I will write the Ex is equal to 5 root x. Is it clear or not? You tell. Now there is a cube, right? This is the x-axis, this is the y-axis, and this is the z-axis. A cube is present over here. Are you getting or not? You tell.
Yes.
Right? And the electric field is in the x direction or not? You tell. this phase, listen one thing, this is the one phase and this is the another phase. The electric field is coming out from this phase, fine,
Yes.
and the electric field in x direction is entering into this phase, you tell. So this is the outward flux, this is the inward flux. Are you getting or not?
Yes.
Can you tell me listen, the electric field is not constant here, rather electric field is as a function of x. So what is the value of x? Here the x is 0. Then what is the value of x? You can see from the figure. It is the value of x over a for this phase. This is the x value is 2a at this phase. Please tell.
Yes, sir.
So can you tell me what is the what is the electric field E2 at this phase? 5 into root 2a. Tell. The x value is 2a. So this is the electric field. And what is the electric field at this phase? X value is a, 5 root a. Is it clear or not, you tell?
Yes, sir.
Tell me, if you consider this is the phase, the area vector is in this direction or not?
Yes, sir.
And what is the area? Total area is what? Say it is square. So area is a square I cap in this direction, or a square, or magnitude you may write. This is the x-axis is equal to a square. What is the theta you will write over here? Say 0 degree. While in this case, the electric field is in this direction and the area vector is in this direction. And what is the theta you will write? Here minus 180.
Minus 1.
Right, this is the 180. So the flux linked with this phase is E2 into S, 5 root 2 into a square. Is it clear or not?
Yes, sir.
While the entering flux is minus electric field minus E1 into S. E1 is what? 5 root a. Are you getting? Area is what? Say a square. So it is minus 5 a ki power 5 by 2. It is 5 root 2, right? A ki power, right? 5 by 2. Please tell, you are getting this thing or not, you tell.
Yes, sir.
So what they are asking? In the part A, what is the part A? They are asking the flux through the cube. Flux through the cube, right? Flux through the cube is what? Phi 2 minus phi 1, or you may write phi 2 plus phi 1. This is the end out flux 5 root 2 a ki power 5 by 2 minus 5 a ki power 5 by 2. Fine.
Yes, sir.
Okay, the value of a is also given 1 meter in the last. So it is 5 root 2 1 ki power 5 by 2 5 1 ki power 1 by 2 root 2 minus 1. Flux unit is right Newton meter square per coulomb. It is approximately 1.41 minus 1.41, right? Approximately 2 Newton meter square per coulomb. This is the flux linked with this cube. You understand or not, you tell?
Yes, sir.
Copy this. So for the B part, the charge in the cube we have to find. So now this is the outward flux. So apply the Gauss's law. What is the Gauss's law, you tell? The outward flux is equal to charge enclosed divided by epsilon naught. So the outward flux is 2. The charge enclosed will be equal to what? 2 epsilon naught. Is it clear? You will put the value of epsilon naught 8.85 into 10 ki power minus 12. This is how much? 1.7 into 10 raised to power minus 11 coulomb. Right. So this is the charge enclosed in this cube. If you know the outward flux, net outward flux linked with this cube, then you can apply the Gauss's law to find the charge enclosed. Right. Copy this. So read this question. in this question, there are two wires. This is the one wire, right? There is another wire, infinite long wire. What it is linear charge density? Lambda 1 coulomb per meter, lambda 2 coulomb per meter, right? And this is x is equal to 0. It is placed a comma 0. It is placed minus a comma 0. Getting? So now you have to find, and lambda 1 is greater than lambda 2. So the point will be this side, right? From x is equal to 0. Suppose this is the y-axis. Where the electric field will be? 0. Why? Because its electric field is more, it is less. So if you assume to be this distance x, this is a plus x. So because of first wire, the electric field will be in this direction or not, you tell. What is the value of the electric field E1? Say 2k lambda 1 upon R1. Say 2k lambda 1 upon a plus x. And if this is the wire 2, so what is the electric field? Say in this direction E2. E2. It is 2k lambda 2 upon R2. What is R2? This distance is what? A, and this is x. So this is a minus x. What, according to question, what is the condition? We have to find the position of this point P, where the electric field is 0. Therefore, these electric field will be equal in magnitude and opposite in direction. 2k lambda 1 upon a plus x, 2k lambda 2 upon a minus x. Multiply a minus x, multiply a plus x. Lambda 1a, lambda 1x. Lambda 2a, lambda 2x. Fine. Lambda 1a minus lambda 2a. X, lambda 2x. Common, lambda 2 into a. So what is x? Lambda 1 minus lambda 2 upon into a. Is it clear or not, you tell?
Yes.
Copy this. So read this question. In this question, semicircular ring. This is the semicircular ring and the charge is given over this ring. All right. And the total charge is what? The total charge is 1.4 into 10 to the power minus 9 coulomb. Right. Electric field intensity we have to find. So do we have the formula for the electric field intensity over here? Do you know the formula?
No, sir.
So we can derive this first, right? So first you will write the concept, right? If suppose this is the charge and it is distributed over this, right? The linear charge density is lambda coulomb per meter. Are you getting? So at distance theta, right? You assume the elemental portion is d theta, and because of this elemental portion, the charge is dq, right? And if this distance is x, so dq is equal to lambda into dx. Fine. And because of this portion, the electric field is elemental dE. In the same way, at distance d, right? At distance theta, this is d theta, right? And the elemental electric field is dE. If you consider this the theta and theta, right? So because of dE cos theta and dE cos theta, so it become 2dE cos theta, 2dE cos theta, and this is the dE sin theta and dE sin theta. So dE sin theta component will cancel. So at this point, due to semicircular ring, right, the electric field will be equal to integration of 2dE cos theta. You have to integrate that. All right, and dE is equal to what? K dq upon r square. R is the radius. So here 2k dq upon r square into cos theta. Fine. And what is dq? dq is nothing but lambda into dx. So 2k and r square, and dq is what? Lambda into dx into cos theta. Right. So lambda will also come out from the integration, and it is dx into cos theta. So now you have to integrate. In this case, suppose this distance is dx, this arc distance is dx, this angle is theta, the radius is r. So angle is equal to arc upon radius we will use. So dx is equal to r d theta. Dx can be written in terms of theta, because inside integration the both variables should be same. So the electric field is 2k lambda upon r square, integration of r, sorry, this is small r, you may write, this is small r square, in place of dx r d theta into cos theta. So 1 r will cancel out, 2k lambda upon r, right? This is cos theta into d theta. And the integration varies from 0 to, tell me, 0 to 90 degree. Yeah, 0 to 90 degree in the semicircular ring. So if you write from 0 to theta, then 2k lambda upon r, right? The integration of cos theta is sin theta from 0 to theta. Right, so this is 2k lambda upon r, you will put sin theta, right? This is the answer. So the electric field due to this uniformly charged ring at this, this is the if this is the ring, for ring theta is equal to what? Say 90 degree. So because of this ring, complete ring, right? Because of this complete ring, the electric field at the center will be equal to 2k lambda upon r into sin 90, and sin 90 is 1. Is it clear or not? Where lambda is equal to total charge per unit length. Per unit length mean total charge per unit length mean this is pi r. What is the total length of this circumference? Is pi r, right? So this is the lambda. Are you getting or not?
Yes.
But for arc, if this is the arc, circular arc, and this angle is theta, this angle is also theta. This is for circular arc. The electric field will be 2k lambda upon r into sin theta. This is for circular arc. So first copy this, right? So read this question. In this question, 4 charges are placed at the circumference like this, right? This is the plus q, this is minus q, this is minus q, this is plus q. So the r end, right? So this is plus q, and this is the force. Because of plus q, the force is this. Because of this minus q, also force is this. Because of plus q, the force is this, and because of minus q, force is in this direction, utal. So the resultant force will be in this direction. Is it clear or not, utal?
Yes.
Right? So what is this time utal? Let me check. This is 6, 7, 8 and 9. So it is 7:30. So I think 7:30 is correct answer or not, utal?
Yes, sir.
Copy this.
So we only have to see the resultant force.
Yes, and its direction.
Except
Right. So the net force due to all 4 charges is acting in this direction, right? So this force is acting in this direction, and if the clock has only r end, so then the result force point the direction. So this is only the time, right, towards the net charge, net force.